Welcome to a new topic. We're going to be talking about conservation of momentum now. And this is another conservation idea, just like we have the conservation of energy. And with this now, instead of energy, where we just had, it was a scalar, it wasn't vector, now we're going to add back in the piece about vectors, because momentum is a vector. And to start with the idea, I want to suggest we think about, let's say there's a car crash, and somebody smashed into somebody else and the two cars get all crumpled up together. Could we tell somehow if the one was speeding? Well, you might say, well, let's look at the conservation of energy, like we had. If one hits and then they both go and move forward. But we can't use conservation of energy because so much energy was lost in heat, in sound, in crumpling up the cars. So we can't use conservation of energy, but the cool thing is, there is another conservation law we can use, and that is the conservation of momentum. Now, momentum, as I said, is a vector. And if you think about what might have more momentum than something else, what factors do you think would be involved with momentum? So take a minute, think about it. What can I do to give something more momentum? If you guessed mass, heavier things, yep. So momentum definitely has to do with mass. Something that is more massive has more momentum. And you probably can guess the other one too, which is velocity. Something that's going faster definitely has more momentum. Now with energy, it was really speed because it was 1/2 mv squared. And so really with energy, it was speed, it was a scalar, it wasn't the vector. Now we're dealing with velocity. Momentum is a vector. Momentum is given the letter P. Don't ask me why. So lowercase p is the symbol for momentum. And it's a pretty darn easy equation. Look at that. I'm just going to remind you, it's a vector because the velocity is a vector. So we've got this idea of momentum and conservation. Okay, conservation of momentum. So what does conservation of momentum mean? Well, like the conservation of energy, you had initial energy plus minus work equal final energy. Without any work added to the system, initial and final had to be the same. And that's how we're going to deal with momentum. We are going to say that the initial momentum has to equal the final momentum. And that's really conservation of energy right there. Not too bad, right? This looks easy. I can handle this. So what are we talking about with momentum? What are our units? What are our numbers? So let's just give you an example. And I have, as you know from my talking about it, I have a little smart car. And it has a very lightweight mass for a car. And let's say that I'm moving at 70 miles an hour. How much momentum do I have? Well, I can't just do 750 times 70 because look at those units. Miles per hour. We got to convert that, and that converts to 31.3 meters per second. There's our happy metric units. So the momentum of my smart car, SC, is 750 times 31.3, which is, it's a big number, 23475. 23475. And what's the unit? It is kilograms times meters per second. And for once, we actually don't have a name for this unit. There is no name for the unit of momentum. Again, I don't know why. I don't know why it's called P. So the unit for momentum, just a kilogram meter per second. It's the kilogram times a meter per second. So let's say I'm going to compare the momentum of this smart car, and I'm going to compare it to the momentum of a semi. So how much momentum would a semi doing 70 have? Well, okay, so a semi, let's see, I'm estimating a mass of about 20,000 kilograms. And again, my velocity is 31.3 meters per second. So for the semi, we actually have a momentum of, this is big, 626, kilogram meter per second. All right, so my smart car doing 70 miles an hour, about 23,000 units of momentum. A semi doing 70 miles an hour, 626,000 units of momentum. How fast would I have to go in my smart car to equal this momentum? So if my momentum of the smart car is 626,000, I gotta get a fresh marker. And my mass is 750 kilograms. What velocity do I need? Go grab a calculator and make the calculation yourself. See how fast my smart car would have to go to have the same momentum as a semi doing 70. Give it a try. What did I get? I got a velocity of 835 meters per second, which, if you do the conversion, is, it's about 1,900 miles an hour. Yeah, let's put a couple exclamation points there. That's kind of fast, isn't it? So, momentum, it's a nice, just straightforward equation. Conservation is like this. Now, this is big momentum. We also can deal with very small momentums. A housefly buzzing around. So, let's say we have a housefly buzzing around. That momentum, let's see, the momentum of a fly. We might have something, oh boy. Actually, kind of the inverse of this. Instead of 10 to the positive 5, we have 10 to the minus 6 kilogram meter per second. And so momentum, we are going to have a huge range of numbers that are possible for answers for momentum, which means that it's a little bit harder for you to guess if something is reasonable. So you'll have to do kind of other checks to find out if an answer is reasonable. You know, if you're finding a velocity, we know what good velocities are. So that's just the idea of momentum. The idea of conservation of momentum is just that the initial has to equal the final. It's conserved. There's no change in it. It's not created or destroyed. We're just going to say initial momentum equals final momentum. And that's the introduction. I hope this makes sense. We're going to have some fun with this because you've already have the idea of conservation. You already know how to deal with vectors. So this isn't a lot of new stuff. It should go pretty quickly. I hope so. Good job.